Recently, I've made a couple of videos about torsion boxes. In the first one, I showed the benefits of using half laps for the inner grid and demonstrated a way to cut those with a track saw. In the second video, I made a torsion box out of very thin plywood and then tested it for strength and stiffness. But what people like about torsion boxes is that they are a way to get a flat surface that stays flat, and I haven't really made anything yet that's actually flat, so it's time to do that. Building a torsion box that's flat is a chicken and egg problem. It won't end up flat unless it's carefully built on a reference surface that already is flat. So in order to build something flat, first we have to build something flat. That's unfortunate, but this is where we are. A common approach is to build a temporary flat reference surface using sawhorses and 2x4s and levels and shims. This technique is demonstrated by Mark Spagnuolo in a WoodWhisperer video from 2009. In most every online discussion about how to build a torsion box, someone mentions that video, so I dare say it's considered a classic. But in that video, Mark credits David Marks, who had previously demonstrated the method in WoodWorks, his TV show on the DIY network, episode 409. Whether you call it the WoodWhisperer method or the David Marks technique, it's considered tried and true, and that's why I'm mostly following it. But there are 3 ways that I'm doing things a little bit differently that I want to show you in this video. I also want to explain how and why this method works. I consistently get better results in my shop when I understand things a little more deeply rather than just walking through a list of steps. So I'm going to cover some fundamentals up front. I found one dictionary that defines the word flat as without marked projections or depressions. A more math or geometry oriented definition would be to say all the points are in the same plane. Here in a wood shop, we use the word flat in a variety of different situations. When we talk about a cast iron machine surface like a jointer table, we want it to be very flat. One way to measure the flatness of a surface like this is with a dial indicator because the surface isn't very large and because we hope that any deviations will be measured in thousandths of an inch. But we can measure the flatness of most any surface by using a straight edge. If there are high spots, the straight edge will rest on them, and the low spots will be gaps between the straight edge and the surface. The size of those gaps can be measured to give us an indication of how flat the surface is. In the case of a jointer table, we expect very small gaps, so we're talking about small feeler gauges. If Lee Valley made a straight edge that was 300 miles long, we could lay it across the state of Colorado and clearly see that all of the Front Range cities are in a low spot. Just saying. If we're building a torsion box, we're usually talking about some kind of table, typically with dimensions ranging from around 2 feet to maybe 10 feet, and made of wood. And we're probably targeting tolerances measured in hundredths of an inch at best, not thousandths of an inch. So because of the size and tolerance, a dial indicator isn't really the right tool. But even with a wood table, we can still measure the flatness by looking for gaps under a straight edge. The concepts of straight and flat are closely related here. Straight is one-dimensional. Flat is two-dimensional. A surface is flat if you can place a straight edge on any 2 points on that surface and have no gaps. We can use straight things to measure the flatness of an existing surface, or we can go in the other direction and build a new flat surface by constructing it from straight things. This is the core of why the David Marks method works. We lay a set of long beams across 2 end beams. If the end beams are straight, and if the long beams are both straight and of uniform size, then there can't be any mountains or valleys along any of the beams. Does that mean that the beams will form a surface that's flat? Almost, but we're not quite there. We've eliminated the possibility of high or low spots along a beam, but those beams don't go diagonally, so the 4 corners might not all be in the same plane. In other words, it's possible that the surface has twist. And this is why both Mark and David in their videos use shims to raise one or more of the corners as needed until all four are in the same plane. Now let me show you my setup and how it differs from the one shown in Mark's video. Mark made the beams out of 2x4s using a jointer and a planer, which makes sense. When you're talking about making things straight and flat and uniform size, the jointer and planer are the go-to machines. However, there are reasons why you might want to make beams out of plywood, which is what I've done. First of all, many woodworkers don't have a jointer or planer. I actually do have those machines, and I still chose plywood, in part because it's more stable. I think I might want to leave these beams in place for quite a while, or even store them away and use them again. Over time, the beams are far more likely to expand or contract if they're made of solid wood. Even if you only plan to use the beams for a weekend, you may be concerned about this issue if you're as grouchy as I am. When I buy 2x4s at a big box store, I assume they might change size significantly during that long 12-minute drive back home. To make my beams, I used a track saw to rip the plywood sheets into strips. Then I face glued the strips together and used the table saw to rip them all to the same width. I used 3/4 inch plywood and laminated 3 strips to make each beam, resulting in a beam that's about 2¼ inches thick. That's probably excessive, but I do like to overbuild things. I went even more excessive when I decided to cut 7 strips per sheet, thus making them roughly 6¾ inches wide each. After running each beam through the table saw twice, the beams end up over 6 inches vertically when they're standing on edge like this, which is almost certainly more than I needed. I admit that I did want them beefy because of concerns about sagging, but I didn't really expect them to end up as wide as they are because I wasn't sure how many times I would have to rip them to get them of uniform size. In fact, I didn't even know whether I would end up doing those rips with a track saw or a table saw. Actually, my original plan was to make the beams 4 layers of 3/4 inch plywood thick, but that was too excessive even for me, and it exceeded the depth capacity of my track saw. I decided to try the table saw first, and I started by giving it a very careful tune-up to get as much accuracy as possible. And when I did the rip cuts, I did them as carefully as I can, using not just the stock guides, but the feather board as well. But even with all of this preparation, I wasn't really sure how the results would turn out. After I ripped all the beams to width, I took a bunch of measurements to see if they turned out okay. If I needed to make adjustments to the table saw and redo the rips, or if I needed to switch to the track saw and use that instead, the beams would get smaller each time I did that. So I planned for that possibility by cutting the strips wider. If you're building a set of plywood beams, I would suggest cutting at least 8 strips per sheet. I'll explain why in a little bit. After you cut the strips and glue them up and then rip them to width with 2 clean edges, check everything carefully. If there are any problems, it's better to find them earlier than later. First, check each beam for straightness using the longest straight edge you have available and the best straight edge you have available. I'm checking here with a 36-inch precision straight edge, and as a second check, use the longest straight edge you can find in your shop. In this case, I'm using a track saw guide rail that's 3 meters long. Another option to check for straightness is to use a 6-foot box level. This is going to come in handy later when we do the flatness adjustments anyway. The next step is to measure the width across the beam as carefully as you can, and you want to take several measurements on each beam. What we're looking for here is how consistent is the width of the beam along its entire length. Are the 2 ends the same width? Also, how consistent are the widths of all the beams compared to each other? Once again, the end beams only need to have the top edge be straight, but the long beams need to be straight and they all need to be the same height when sitting on their edges. You want these measurements to be as accurate and precise as possible, so really The best choice is a caliper. This is why I suggested you make your beams at least a little smaller than I did by cutting at least 8 strips per sheet instead of 7. A plywood sheet is 48 inches wide, which means 8 strips will make each one just under 6 inches. And here's the thing. A 6-inch digital caliper is fairly inexpensive, but 8-inch calipers are less common and they cost more. By cutting these beams as wide as I did, mostly what I accomplished is pushed them just beyond the range of my caliper. After checking and measuring all the beams, if you're not happy with them, you can adjust your tools or technique and rip them again. In my case, the results from my initial rip cuts were good enough that I am not motivated to try and improve on them. I took 31 different measurements of the width at various places on these 4 long beams. The difference between the smallest and largest measurement is just over 1/100th of an inch. If I ripped them all again, I honestly don't know if I could get a better result, and it might turn out worse. The second thing I've done differently here is to use leveling screws instead of shims. In Mark's video, the sawhorse is the end beam, and the adjustments are made by placing shims under the legs of the sawhorse. In my design, the end beam is just one of the plywood beams I made, and I've attached a side-mounted leveling foot at each end, the kind that can be adjusted with an Allen wrench from above. By the way, I made all the beams 8 feet long, which is the full length of a plywood sheet. The end beams might not need to be that long because it would be unusual to try and build a torsion box larger than 4x8. In fact, I've currently got this set up with only enough long beams for a 4x8 sheet, and there's an unused section of end beam over on this side. But I went ahead and left the end beams full length in case I want to make a really big surface, because I didn't see any compelling reason to cut them. As I said, the David Marks technique is considered tried and true, and using shims will obviously work, but I personally find shims to be somewhat unappealing. The necessary adjustments to make this surface flat will require trial and error, and there's no way around that. But trying to make fine adjustments by turning an Allen wrench just seems so much less painful. Because of the way I'm using these leveling feet, my 2 end beams can be placed almost anywhere that provides a firm resting place. Even the floor would work. I ended up using sawhorses anyway because it was the easiest way to get the height I wanted, but I considered other options, and you can choose whatever works for you. So I've made the beams, and I've set up a way to make fine adjustments. Now, how do I make those adjustments in order to get everything flat? This is the third area where I did things a little bit differently. I start out the same way that Mark showed in his video, using a level. The basic idea is that if all the beams are level in both directions, then the surface has to be flat because everything is in the same plane. By the way, strictly speaking, it isn't necessary for the surface to be level in order to be flat. Making it level is just one way of making sure that everything is in the same plane. And also, we probably want our reference surface to be more or less level anyway. Box levels aren't terribly expensive, so I like to put one on each side of the surface. It's not actually necessary. You can use just one level and move it around as you make adjustments. It'll just take longer. To be honest, I don't like bubble levels very much. I'm always wondering if I'm reading them correctly. Is that bubble really centered between the lines? And while I'm whining about bubble levels, let me just say this. Inexpensive bubble levels don't have very good sensitivity. When I make a half turn of the leveling screw in one corner, I'd like to see that change clearly reflected, and it's not that easy to see if any or all of the bubbles moved. Like I said, I do want my reference surface to end up fairly level anyway, so I do use bubble levels as part of my approach. After getting everything as level as possible, Mark and David both used winding sticks to verify and finalize their adjustments. Winding sticks are a classical approach that has been around for centuries. Basically, they're a way to make the twist in a surface more visible. I have winding sticks in my shop, and they have their place. This is a nice set from Lee Valley. But to be honest, I like winding sticks even less than bubble levels. Instead, I've used a technique called crossed strings. I first learned about this method from a write-up by Jamie Buxton based on a talk he gave at the Bay Area Woodworkers Association in May of 2002. In a nutshell, you run a taut string along each diagonal, crossing in the center, and then make fine adjustments until the two strings just barely touch. The reason this works is based on math and geometry. In order for the resulting surface to be flat, we need all four corners to be in the same plane. And one thing we know from the world of math and geometry is two lines in 3D space are coplanar if they intersect. Admittedly, I like this method because I'm a nerd, but even for normal people, it's worthy of consideration because it's easy and inexpensive and very precise. I'll go ahead and walk through the crossed strings method in a bit more detail. You need some monofilament fishing line. I used 12-pound line, which has a diameter of 0.14 inches. And you need 4 spacers, all the same thickness. These are used to raise the strings high enough that the beams won't interfere with them. I used auto body shims, 1/8 of an inch thick. You can get these at an auto parts store or Harbor Freight or whatever. And while you're in the automotive section at Harbor Freight, get a set of feeler gauges. You want the cheapest set you can get because you're going to cut the one that matches the diameter of the fishing line. I'll explain the purpose of this in a bit. Finally, you need 4 weights, each one a bit less than half the tested weight of the fishing line. These are used to keep the strings taut. You want the weights to be heavy enough to avoid any significant sagging in the strings. Since I chose 12-pound line, I should be able to go up to 4 or 5 pounds or so, but I used a set of horseshoes that were handy. They're 2 pounds, 7 ounces each. It's best to use the same amount of weight on all 4 corners because if the strings do have any sag, we want the sag to be the same. Use a handsaw to cut a very small notch near the end of each diagonal. We'll place the string in that notch just to keep it from slipping. Measure the distance between the corners, add a bit more for dangling the weights, and cut 2 lengths of fishing line for the 2 strings. Tie a weight to each end of both strings. Run the first string across one of the diagonals, placing it into the notches at each end. This will be the lower string. At each end of the string, tuck one of the spacers under the string on top of the beam. Now run the other string in the same way. Insert spacers for this one as well, but we want this one to be the upper string, so it needs to be a little bit higher. How much higher? Exactly the diameter of the fishing line, which is why we bought the cheap feeler gauge. Find the feeler gauge that matches your fishing line, in my case 0.14 inches, and go ahead and cut it right off. And slip 1 piece under each spacer of the upper string. Now look at the point where the strings cross in the middle. You need to start with them not touching, which means there should be a gap between the upper string and the lower string. If they're touching, raise the upper string or drop the lower string by turning the appropriate leveling screw until there is a gap. Then adjust 1 or more of the leveling screws a little at a time until the strings just barely touch and no further. You don't want the strings putting any pressure on each other because if they do, they won't be straight anymore. The crossing point of the strings can be a little hard to see. I've experimented with a flashlight and with holding up different colored things as a background to get more contrast. How many leveling screws need to be adjusted? And which ones? It's a bit counterintuitive, but if you don't care about keeping the surface level, you only need to adjust 1 leveling screw, and it doesn't actually matter which one. Stepping again into the world of math and geometry, we know that 3 points determine a plane, and we only have 4 points, so there's only 1 extra. So in theory, you can always make the beams form a flat surface by adjusting just 1 leveling screw to raise or lower it and make it join the plane defined by the other 3. In practice, that may require more adjustment than the range of the leveling foot, which is only about 1 inch or 2 somewhere in there. Also, adjusting just one leveling screw might result in a surface that is further from level than we would like. So you'll probably want to adjust multiple leveling screws while keeping an eye on things with one or more levels. As long as the levels don't interfere with the crossed strings, you can keep them in place during the adjustments so that you can keep an eye on both things. Now that the adjustments are complete, all I need to do is take away the levels, remove the strings, their weights and the spacers, lay a sheet of MDF across the beams, and I'll have a flat reference surface that I can use to build a torsion box.